Hello. In this segment, we're going to be talking about practical TCP, IP, and Ethernet, and in particular, the addressing components and end-to-end delivery of protocol data units. Recall the TCP/IP model. Each layer is going to have its own particular protocol. So, for example, in a web application, layer 7 would be the HTTP protocol, layer 4 would be the TCP protocol, layer 3 would be the IP protocol, layer 2 could be potentially Ethernet, and layer 1 could be a voltage that's on a wire. Data is encapsulated as it moves from higher to lower layers and decapsulated as it moves from lower to higher layers. And so these are the protocol envelopes in which the data is placed. The key idea is that each layer has its own component of an address that is going to identify uniquely an endpoint of communication. Let's look at an example. In HTTP, the unique portion of the request that has the address is the URL that we will be visiting. And of course, we'll also have a response that comes back as well. At layer 4, we find TCP. TCP consists of a number of different fields, all of which contain various bits. Let's examine some of these. Here is the component of the address of which we're interested. The ports indicate an application that is listening on a particular host. So web servers listen on port 80, and web browsers are going to ascend from ephemeral ports that are in the range of 49,152 to 65,535. But there's both a source and a destination port that are indicated. We have 32 bits each of sequence numbers and acknowledgement numbers. And these allow the stream to be reconstructed in the appropriate order, and dropped packets can be retransmitted. We also have a series of flags such as SYN and ACK and FIN and reset. These flags allow for initiating and closing connections and synchronizing sequence numbers and acknowledgement numbers. We have a window size that allows for flow and congestion control. The larger the window, the more data we can have out on the wire that's unacknowledged. At layer 3, we also have various portions of an address. In particular, we have the source and destination IP address, each of which is 32 bits. This is globally unique so that a particular packet can reach a particular computer system on the internet. At layer 2, again, we have more bits. The ones we're interested in here are the source and destination address, each of which is 48 bits. This is a unique hardware address called the MAC address, the Media Access Control address. And in this is for transmission on a single network, the next hop destination on the network. And so summarizing here, layers 7, 4, 3, and 2 have these protocol data unit names that are data, segment, packet, and frame, and the address portions are things like URLs, ports, IP addresses, and MAC addresses. It's interesting to note that common intermediary devices that we find work at different layers. So proxies, for example, work at layer 7 and 4. Routers and firewalls tend to work at layer 3, and switches work at layer 2. So each of these understands a different portion of the address. I want to spend a little bit of time talking about IP addressing. 32 bits is typically divided into 4 different octets. This is why if you look at the dotted decimal notation, you see numbers like 192.168.5.4. The dots separate the different octets, or groupings of 8 bits. There's an arbitrary dividing line that we find in any IP address that separates the address of the network from the address of the host that's on the network. So here we see an example of 28 bits that are set aside for the network portion. And this is what's important for routing. And then we have 4 bits that are specified for the host portion on the final network. And this is for the last hop delivery. And so in this particular example, we see what's called a variable length subnet mask, VLSM, of /28, indicating that 28 bits are set aside for the network portion, and the remaining 4 bits out of 32 are set up for the host address. This would correspond to a net mask of 255, 255, 255, 240, which is all 28, the first 28 bits as ones and the last 4 bits as zeros. So, how does data move through a network? Let's look at an example of end-to-end communication for a web request. So step 1 is that the PC wants to send a web request to the server at 65.215.65.132. The PC looks at its own IP address and compares its network portion against the network portion of the destination. And it realizes that these are on different networks. And so, since they're on different networks, it will need to be routed. So, the PC is going to use its configured default gateway and send an ARP request to figure out what is the hardware or MAC address of the router that it wants to forward this packet onto. The router is going to then respond with its MAC address. This is a hardware address on the same network. Step 3. The PC is going to take the HTTP data, it's going to encapsulate that in a TCP segment, it's going to put that into an IP packet with the web server's IP address in that packet. And then it's going to encapsulate that in an Ethernet frame. But that frame does not have the hardware address of the final destination. It has the hardware address of the next hop. That is, the router that it's going to be forwarding the packet onto. And then it sends it. The switch then receives the frame, the layer 2 frame, and it's going to examine the destination MAC address. Switches have switching tables. It knows which ports contain which hardware devices on the other end. So it's going to look up the right port to send it out, and it's going to forward it on to the router. The router is going to receive the frame and remove the layer 2 frame to examine the destination IP address. It will realize that it's on a different network, and so it will forward it on to its gateway. And so on, and so on, and so on, through all the intermediate hops on the network. All of these are looking at the layer 3 address and figuring out where to route that packet. Finally, it reaches the destination network. The border router is going to receive this packet, and it's going to recognize that the destination of that packet is on its local network. The network addresses of the destination and the router's address are the same. It then is going to send an ARP request for the MAC address of the server and form a layer 2 frame with the server's MAC address in that. The switch receives that frame, it looks up the MAC address of the server in its switching table, and it will forward it out the appropriate port. On the final end here, the server receives the data, strips the frame, the packet, and the segment, and transmits the data itself to the application that is the web server. And then this process is reversed in order to send the reply back across the internet to the original sender. In summary, each protocol data unit contains addressing information. Segments have ports, packets have IP addresses, frames have MAC addresses. IP addresses are going to be divided into a network portion and a host portion using a variable length subnet. MAC addresses form the basis of a single hop between directly connected devices. IP addresses connect hosts that are on different networks. Segments then connect applications on each host using the port. Switching happens at layer 2, while routing happens at layer 3.